And just about 2 years back, the Nobel Prize, one half of the Nobel Prize in 2019, was actually given to Michel Mayor and Didier Colletts for their discovery of the first exoplanet orbiting a sun-like star. And this discovery was actually made by them way back in 1995. But we'll come on to why is it that people took so long to actually be sure about these detections of exoplanets, and why is it so difficult, and what was the issue in doing that. So let's start off with a long time back when Giordano Bruno, said that he himself had a vision that the space we declare to be infinite, in it are an infinity of worlds of the same kind as our own. So it was already expected way back that probably we do have a large number of worlds which are there in the universe, and it's just a question of actually looking for it. But obviously this was something that was not liked by the church, and Bruno actually paid with his life for this and for this statement of his. And so exoplanet was actually one of the most eagerly awaited discoveries, where searches went on for decades. Many teams, many stars, many different techniques. They actually tried to look for exoplanets, but this was without success. And what was the problem? Were the techniques not sensitive enough, or was it that there were no planets at all? And the first possible evidence is something that number has gone, but about more than 100 years back, almost 75 years back. And the first confirmation of detection was in 1992. And it would be interesting that this was actually around a pulsar, which was the first confirmation of detection. And as of January 2022, we have about 4,900, or like I said in the beginning, the updated list today is almost 5,000 exoplanets, which are actually listed. Now let's focus upon the detection techniques. Why has it been so difficult to actually look for exoplanets? And I'll talk about the methods used in detail. But if you look at this plot on top, you can see it's like finding a needle in a haystack, because I'll explain to you why. So the most standard adopted techniques are, one is called the radial velocity technique, which was used by the team we spoke about, Michel Mayor's team. And there's the other method, which is the transit method. And I'll tell you about both of these. And you can see that initially the radial velocity method was the method that was used. And later on, you have a big surge in the numbers increasing using the transit method. But I'll even explain to you why do we suddenly have this surge. The other methods looking for exoplanets are the ones using direct imaging, microlensing, transits, and timing studies, etc. So like I said, the standard methods are through radial velocity, through transit photometry, microlensing, and direct imaging. Now, the radial velocity method, the simplest method, is the one which basically is depending on gravity. So let's assume you have a planet going around a star like this. They're going around their common center of mass. So the green square you see is the center of mass, and the star and the planet are both going around the center of mass. And what you would actually see, if you were looking at the star from here, you'd actually see a wobble in its position, right? Because as it's going around this system, in terms of its position as well as in terms of its velocity. And this can be actually used to find the period of the orbital period of the companion. And in that way, radial velocity can be actually used to look for this. A better demonstration you can see of it over here. Here again, you have the star and the planet going around their common center of mass. And if you were to actually see it in terms of speed, if you were observing from here, from this side, you'd obviously see this blue star moving. This is not the star, but this is the planet. The blue dot is the planet. And you see the planet going this way, back and forth, right? So you'll see a wobble or a movement in the position of the star as well as the position of the planet. Along with that, since the planet is coming towards you and away from you, you can see this kind of a trend in the terms of the speed, right? The velocities. So you'll get this kind of a wave, a sinusoidal kind of a wave, which is coming over here. And one way of detecting this is through spectra. So supposing you look at the spectrum of the star, right? This is the star. The star is coming towards you and the star is going away from you. So if you have a spectral line, and the dotted parts are the lab values for the spectral lines, the wavelengths. And you can see that the spectral line is going towards the red and it is going towards the blue. So it's going towards the red when it's going away from you, and it goes towards the blue when it's coming towards you. And therefore, one method in the radial velocity is you actually look for the wobble, which is very difficult to look for. And the other way is through spectroscopy. That means you take the spectrum of the star and you look for the shift in wavelengths, the delta lambda, which will actually show you what is the change in this position, right? Now, so if you look over here, you can see that there is this Doppler shift which is coming because of the stellar wobble. And here you have this happening over here. And just for your information, if you were actually looking at Jupiter, for example, Jupiter would barely give you a thing of, if you were to observe from 5 parsecs, you were to look at Jupiter moving around the sun, you would actually get a variation of about 13 meters per second. Okay. And the variation which will come from the Earth will be only about 1 meter per second. And the best telescope just now we have the best spectrometer, which is on the HARPS, which is on the ESO 3.6 meter telescope, that can actually measure a 1 meter per second kind of a variation. So ideally, you could have actually detected Jupiter, right? But so essentially, this is what that Geneva team, the Michel Mayor team, which is basically from the University of Geneva, what they actually did is that they measured this kind of radial velocities. So what you're seeing is this is in terms of kilometers per second, but they actually got this kind of this thing. And here you can see that this is the kind of precision you require in your measurements. The other problem with radial velocities is that you are looking at this system from here, for example, from this foreground, and based on this, you are getting this thing, but you do not know exactly what is the inclination of the orbit, right? So if you are very lucky, then the orbit is perpendicular to, is perpendicular to the line of sight, to your plane of vision. Then in that case, you'll get the best effects. But otherwise, you will actually have a projection, right? Depending upon what is this angle. And because of that projection, your measurement, which you're going to get of the mass of this thing based on using Kepler's law for this thing, you're basically going to get a measurement of m sine I, okay? Where I is the inclination of the orbit and m is the mass. So what you're actually getting is you actually measure the lower limit of the mass when you're using radial velocity method. But this is the method, like I mentioned, which was used by Michel Mayor and Didier Queloz, which is the University of Geneva method, where they actually detected an exoplanet around this star, 51 Peg. This is the constellation called Pegasus, and in that, this was this object. So, like I mentioned, if you were to actually look at Jupiter at a measurement of 13 meters per second, this would basically mean that you're actually looking for a wavelength shift, the delta lambda, right, which you're looking for, is approximately of the order of 10 power minus 14 meters. Okay, that's the kind of measurement precision you require of your delta lambda. Okay, so that will actually give you the kind of the kind of resolution you need for your spectrometer, so that you can actually measure something of this kind. And that exactly explains what I was talking about in the beginning, that why did people take so long to actually discover exoplanets? For the simple reason that exoplanets, you could not, the precision required in the measurement was really very difficult to achieve, right? People could not measure them. And therefore, in 1995, this is when they actually defined this thing. But what they found actually, Michel Mayor and Didier Queloz, what they actually found a giant planet. Okay. Another thing is that in this kind of measurements, obviously your measurement is going to be biased. So like what they found is they found it for a giant planet, which had a 4-day orbit. Okay. And and what was strange about what they discovered is that this planet was a giant planet of this Jupiter types. Okay. And it was twice the size of Jupiter, but it was 7 times closer to the star than Mercury is to the sun, right? So that's why they were very confused about the result they had got, and for a long time they were doubting it whether they actually discovered this planet or no. So actually, it is said that in their paper, the paper which they wrote about the thing, they actually spent more effort in trying to rule out all the possibilities before coming to the conclusion that they had actually detected a planet. Okay, because this was a strange planet, twice the size of Jupiter, 7 times closer to its star than Mercury. And the idea was that a Jupiter-like planet cannot form so close to its star, okay, because the gas, etc., will not, it be too hot for it to coalesce. So generally what's considered is that planets can form from gases if they are beyond what is called the snow line. The slow line is the line, the distance from a star at which you can have snow, simple as that. So at which water will freeze. So if you are closer than that, then it is expected that the gases which are there in the in the planet which is forming will not be able to form. So, but fine, they came to conclusion that this is a planet, and they had detected a planet. So the question was, how could such a massive planet form so close to its star? And so the one of the explanations was that probably it formed somewhere further away, and then it came inwards because of some reason. And this was actually very counterintuitive to what we also think about the formation of our solar system. And therefore the possibility was that this Jupiter like planet formed further away and actually came closer later. So that this actually gives us hints on what we know about our own solar system. In our solar system itself, we know that there has been a process of planetary migration. That is, the planets with the positions at which we see the planets today, that is not the original position at which these planets formed. Okay. So, what we actually know is that when planets form, they can actually create waves and they can actually move inwards and outwards. So, in our solar system itself, there has been a reshuffling of planets where planets have come back and forth, like you can see that, for example, Saturn forming here and then moving here, etc. There's been a kind of a reshuffling in our solar system itself. So that's the power of the radial velocity method, which they actually used to detect exoplanets. And till around 2012, this radial velocity method was the most popular method used for looking for exoplanets. But after 2012, there was a change because we had a satellite called Kepler, which was launched. And that started now looking for planets using another method called the transit method. Now, the transit method, I'll talk to you in a minute, is actually distance independent, but you obviously need high signal to noise ratio. And therefore, it works very well for stars which are within 160 light years from the Earth. And as well as for, looking for massive planets, right? The massive ones are easier to detect. And if your star is lower mass, it's better because the star will wobble more. So what you would like is to have a low mass star, a large planet, and the star, what happens is stars rotate. And as stars age, their rotation speeds fall. And therefore, fast rotation. Generally, a star which is on the main sequence rotates very fast. When it moves away from the main sequence, it slows down. And therefore, fast rotation, and therefore it's better to have a star which has moved away from the main sequence, hence it's slightly slower, and hence detecting its spectrum to get the velocities makes it easier. The radial velocity method also has some problems that, for example, you could have false signals. Supposing if you have multi-planet, multi-star systems, you could have a bigger problem in trying to characterize the spectrum and actually getting the delta lambda and hence the velocity values. And therefore, the transit method is a far more powerful method because it can rule out false positives and actually give you much better data. So let's talk about the transit method. The transit method basically means simple. Here you have a star, there's a planet which comes in front of it. And therefore, if you were observing the star which has a certain brightness, you'll see a certain dip in the brightness of this star, right? And that is what is the transit method, a dip in the brightness. Now, if we actually look, this is just to give you examples. Supposing if you had a G dwarf star or an M dwarf star, the thing is, the difference is depending upon the depth. This is what we were talking about, this depth in the light curve, right? How much of the brightness will fall. It basically depends upon the difference in the ratio of the areas of these two objects, right? The area of the star and the area of the planet. So for example, if you have this depth, it is, your pi r squared for the planet divided by the pi r squared of the star. So therefore, if you actually look for the depth, it's the ratio of the squares of the radii. And if you were to actually look at, for example, the Sun-Earth system, if I just substitute for the radius of the Sun and the radius of the Earth, you're going to get a factor of 10 power 4. So what's going to happen is your brightness is going to fall just by a factor of 10 power 4, which is 1 part in a 10,000th, right? So just think of it, it's as though you had 10,000 bulbs, right? And of the 10,000 bulbs, you just switch off one bulb, okay? And that is the fall in brightness which you have to detect if you want to observe a star through transit, right? And therefore, transit method is very difficult because the ratio, right? This ratio, it makes it more difficult. If you had a smaller star, like an M dwarf, then in that case, the radius of the star is much smaller. So you can see the ratio of the two sizes is, a little easier. So you have a bigger dip. But if it's a G dwarf, you actually have a very small dip. So if we can actually look, just for example, this is using Kepler satellite, you can actually get light curves. These are called light curves. Light curves tells you the change in brightness of the star. So for example, this is an exoplanet called HAT P7b, and this planet is actually a hot Jupiter, and it transits, comes in front of the star, and therefore you get a fall. But if you actually have a look at the numbers over here, just look at this. This is the constant brightness of the star, and here is the dip. The dip is coming in the third decimal place, 0.006, right? That is the kind of depth you're getting. So, the depth of this dip. So it's therefore very, very difficult for you to measure this because this is very small, right? This is coming in the third decimal place, 0.006, right? So it is 0.6% of the brightness. Now, the condition that is put that to actually detect a planet is you should have a dip of at least a 1%. A 1% dip will be an indicator of a planet. Minimum, you should have 3 transits. 3 times you should get this kind of a dip if you want to state that you have actually observed a planet. Now, using that, you can actually get the size of the planets. People actually, you can fit this to various curves to actually get numbers of planets, because there could be a chance that you have more than one dip. You could have 2-3 dips depending upon how many planets are going around that star. And you can measure the orbital period as well as the inclination, right? So this is the example of HAT P7. There's another exoplanet over here. I'm showing you, this is just using a 16-inch telescope, not a very big telescope. And in this 16-inch telescope, you can actually see, this is the exoplanet around WASP 33b. You can see you're getting this kind of a slight dip, and which could be a detection of this thing. So this is using a transit period of 1.6 hours for a depth of 0.03 magnitudes. Magnitudes is the brightness scale used in astronomy. So you can actually get this and see the kind of dip you are getting, right? And that's the kind of precision which you actually need when you're measuring it. Now, the other method which is used for detecting a planet is what is called microlensing. So what happens is, if a star is orbited by a planet, right, you know that through the gravitation of the planet, you will have a lensing effect. The lensing effect will deflect the light. And because of that, you actually observe, you can observe, see, this is the star. And as the planet comes in the front, you have the deflection, due to which you'll have an increase in brightness of the star, right, a small bump. And if the deflection is strong enough, you'll actually see 2 stars, right? It'll a lensing effect with 2 stars, or it'll be split, right? And that's what is called microlensing. So if you have it over here, you see here's the star with the planet, and you can see that as the planet comes in the front, you'll get a slight increase in brightness from a further star. So you have this star, and you can actually get this, and you see that this brightness has this thing. You can look at it in this other one also. Here you have this coming, and you have a slight increase in brightness. So in this case, it doesn't get fainter, it actually gets a little brighter when you actually see this, right? So a microlensing, but microlensing again is very difficult to observe, because this difference in brightness is obviously going to be very small, because you know that the planet doesn't have a very large mass, and therefore the kind of bump it's going to create is also going to be very small. It's not going to be very large, right? And therefore it's difficult with microlensing. The next method which I had shown you is the one which is called direct imaging, right? So let's assume you have a star over here, and you can actually image the planets around it, right? But this thing is a very difficult method, for the simple reason is that the star is very, very bright. Planets are not, they just have reflected light. They don't emit light of their own, right? And therefore what happens is, the star is going to be so bright that in its presence you will not see the planet, because the planet is much, much fainter compared to the bright star. It's like, for example, if you try to look at Mercury, you almost cannot see Mercury because it's so close to the sun that it's, kind of drowned in the brightness of the sun. So you cannot see it, right? And so for example, if you were even seeing Jupiter's sun at 5 parsecs, it would have an angular separation of less than 1 arc second. But still, we have about 100 planets that have been confirmed in 82 planetary systems using direct imaging. So let's see, what is the method which is actually used? What is the way out of this problem when your star is so bright? How are you going to actually see these planets? So here I'm just showing you a telescope image, for example. This one is of Saturn. And you can see that here, what is put is called a coronagraph. That means, see here on the right, you can see this is an image of a solar eclipse. In a solar eclipse, what happens is the image of the sun is covered by the moon, and hence you can see the corona of the sun. And hence that's called a coronagraph. But in the case, you can artificially also create an eclipse by having a corona. This is in the telescope, you're covering up the light, say from Saturn. So if I cover the light from Saturn, I can actually see the ring of Saturn and I can see the planets of Saturn. Similarly, this is done for looking at the sun. There's the SOHO spacecraft which actually looks at the sun. It actually has a coronagraph with which it can cover the image of the sun so that it can actually observe these other, it can observe the corona or the outer A region of the sun. So here you can see, I'll show you an example. Well, here you have this star. And if I want to actually see the planet which is around it, oops. Yeah, you can actually see that if I want to see the planet around it, you see I cover the star and yeah, I can see the planet, right? So by covering the star, I can see the planet, right? So this is a coronagraph. You're basically just getting a thing to cover the star. And if you can cover the star, then there's a planet sitting over here, which was invisible, right? But you can actually see it when you cover the star, right? So I cover the star and I can see the planet. So this is the method which is used for direct imaging of planets. And it is being applied with a lot of these things. So this is using the Keck telescopes. They actually use it to find, you can see these are the 3 planets around this star. You can look over here. This is a VLT, very large telescope image, where it's actually, you can get it over here. And there's another one which has a coronagraph, which will actually, the HST, to actually look for this thing. So direct imaging is also possible, not very easy, but it is possible. So here are examples of some more stars for which we actually cover it and actually look for the planets. Here is the other one I showed you. So these have planets at a distance of about 20 AU. AU is an astronomical unit, which is 150 million kilometers, the distance from the Earth to the Sun. And this is about 20 times that. And you can actually detect these planets, right? This is another planetary system, Beta Pictoris. This is a star where you can actually put a coronagraph. And if you look over here, you can see this is the star. But here you can see B. This is the planet going around it, right? So you can actually use direct imaging to actually look for exoplanets. Now, I also spoke to you before this already about the Kepler mission. So the Kepler mission is the reason for this rise. You can see you have the sudden rise in the number of exoplanets detected using transit method, which I just spoke about. This is because there was the Kepler mission. The Kepler mission was launched in 2009. And it basically has a big telescope out in space, 1.4 meters, basically because you want the telescope to go in space so that you can do photometry much more with very high precision. On the Earth, what happens is because of the atmosphere, you lose out on precision in magnitude measurements. But while if you go out in space, you can actually, you reduce the effect of the atmosphere. And therefore, this was a dedicated mission just looking for exoplanets. It has a field of view which is only about 115 square degrees, which is about a fist at arm's length. Okay. And what Kepler did is that Kepler just stared at the same, this is a Kepler field of view. It just looked at the same part of the sky all the time, right? And this was a region selected which was out of the ecliptic plane. So Kepler started off with this mission in 2009, but then there was a problem with Kepler. There was some problem with the reaction wheels, due to which Kepler was slightly, changed. The mission control was slightly changed, and it was then named the K2 mission, which is the sequel to Kepler, which did not have the capabilities of Kepler, but it was good enough. So that also worked. It worked for some time, from 2014 to 2018. So for 4 years, you had the K2 mission also. So that's it. And then after that, NASA launched another satellite called TESS, which is the Transiting Exoplanet Survey Satellite. TESS actually looked at a part of the sky which was 400 times larger than the part which was observed by Kepler. It was launched about 4 years back, and test data is also available. Now, just for the benefit of students, I would just like to tell them that data from Kepler, K2, as well as TESS, the data is freely available on the internet, okay, on the NASA website. So on the NASA website, on the Space Telescope website, you can actually get data for Kepler as well as TESS. And here there's an example of a student who's a PhD candidate, a PhD student, who actually found 17 new exoplanets using Kepler data. And there are various citizen science projects, planet hunters, etc., with which people who have no knowledge also of science or coding and all, they can actually look for exoplanets, because there is so much of data that we've actually got from Kepler as well as TESS that it is much more than the amount of data that the astronomy community can handle. And therefore, it's very essential that we get some help from citizen scientists as well as others. For student projects also, there are a lot of student projects which you can actually do using Kepler data as well as TESS data. We don't have the time to talk about that today, but if somebody is interested, any of you all are interested, you can definitely do projects using Kepler data as well as TESS data, which is essentially light curve analysis. You will see the light curves which you get for various stars using Kepler and TESS data, and actually use that to identify the stars which actually have exoplanets. Okay, and these are very important things, because these are the potential candidates which are going to be used, for example, by the James Webb telescope. James Webb does not have the time to scan the whole sky. So what James Webb is going to do is going to look at only potential candidates. So if the candidates are already identified using some other means, right, then James Webb is actually going to look at those candidates, the targeted candidates, and look for them. So what is basically being done is we are using all this data to chalk out candidate exoplanet stars or potential stars, which can be observed, for example, with James Webb or any other telescopes, ground-based or space-based, right? So there's a lot of potential for projects with Kepler as well as TESS data. You can also look for planets using, for example, radio data. So this is just an example of one of our publications which actually used radio emission from a star to actually identify a planet. Now, this is a very hot topic in astronomy, exoplanets, and many people are actually very keen on it, in not only astronomers, but also space agencies. And therefore, for example, the NASA missions, Hubble, Spitzer, Kepler, TESS, all of these were dedicated missions, essentially, which also, I mean, they had Kepler and TESS was pure exoplanet. The others looked for exoplanets. And here you have the ESA missions. Even James Webb is going to characterize exoplanets, as well as there's this Plato mission. There are a lot of missions which are actually planned, some of them dedicated only for exoplanets, and some of them which will observe exoplanets other than the other things which they are going to be observing, right? So let us, I'll need to hurry a little bit. Let us now see what are the different planet types which we actually find. So the first planet type which we actually find are these gas giants. And the gas giants we find basically because they are the easiest to detect, right? So if you have a giant star, obviously you will see it very nicely in the transit method as well as in the radial velocity method, because it's a huge one, right? And that's the gas giant. You could also have super Earths, which are quite like the Earth, but are about 3 times larger than the Earth. You could have planets which are Neptune-like, gaseous worlds around the sign of Neptune, or you could have rocky worlds also, terrestrial kind of worlds. So there are different planet kinds. If you actually, you can see this plot over here, which we have, which is of different exoplanet populations. That is the different kinds of exoplanets we know. So there are some which are hot Jupiters. So hot Jupiters, they are obviously large sizes, hence they are up here. And because they are hot, this is, the orbital period is about of the order of a few days. You could have cold gas giants, right, which are cold, but not, so they are further away from the star. And therefore, the orbital period is larger, right? You all remember Kepler's law, T squared is proportional to A cube. So if you're, for example, going to be further away from the star, you're going to be cold. But then in that case, the period will be large. So the short period ones are the ones which are hotter, and the long period ones are the ones which are, colder. Similarly, lava worlds are ones which are very close to their stars. So they have small orbital periods and they're also very hot. You could have rocky planets like this or ocean worlds. And there are different techniques, all these different techniques which are used to actually find them. If you actually see that Kepler discovery space, that means the kind of exoplanets which were found by Kepler, you can actually see that the yellow dots, right? The yellow ones are the ones by transits. So the bulk of them are all transit because Kepler actually is looking for transits. And then you have these blue dots, which are the radial velocity ones. And you can clearly see in this case that there's a very large number of them which are in this region. If you put it in terms of radii, this is Earth radius, Neptune, this is Jupiter radius. So you can see that radial velocity very nicely finds large radii, massive stars. While in this method, you can actually identify smaller planets also. If we actually see it in terms of sizes, right? These are different sizes in our solar system. This is in ratios of the number of planets of Earth. You can actually see them that they range in this way, right? This is actually, I'll come to it in a minute, where you'll see that the bulk of these things, the most common planet sizes, right? If you collect for biases, are actually those which are 1 to 3 times that of the size of the Earth, right? This is the part where you will have maximum number of exoplanets, right? Another very important plot which we need when we study exoplanets is the mass-radius relationship. Why? Because the mass-radius relationship will define density, right? Because it's mass by volume. So therefore, the volume will get defined by r cubed. So if you take m by r cubed, you're going to get a measure of the density. And so if for an exoplanet, you know its mass and its radius, you can have an estimate of its density. And based on that, for example, here you can see that there are various curves for different compositions. Supposing the exoplanet is made up of hydrogen or hydrogen helium or iron or whatever combinations, you can actually get a plot, and depending upon the position on the mass radius plot, you can actually specify what should be the density of the planet, the exoplanet. Here I'm also showing you a plot of do we know about period versus mass, period versus radius. So you can see that here, this is Mars, this is the Earth, this is Jupiter. What you can see is that you do have a large clump in this region and here. And what you see, the most interesting part, is that the observations of the data we have, our solar system planets do not seem to be in this kind of planets which we find, right? And I'll come to that in a minute. If we actually want to estimate the number of Earth-sized planets in our galaxy, right? We know that they are approximately, I hope you all know, but there are certain spectral types of stars, right? And if a star is too hot, right, then in that case, that star actually cannot maintain a planetary system because it's too hot. It will evaporate all the rocky material in its neighborhood. So therefore, we need the star to be slightly colder. So it can be a star like our sun, or even colder than our sun, which can actually have a planetary family, right? And therefore, if we actually say that about 100 billion stars in our galaxy would have the spectral types like the sun or cooler than that, then if these 1/3 of them had planets, we can say about 30 billion of them have Earth-sized planets. And if you say that you're taking even slightly bigger planets, 1 to 3 times the mass of the Earth, then there could be a little bit more, right? And therefore, planets of roughly the Earth size are numerous, right? And that's a very important thing to keep in mind. So here is the same plot I showed you earlier, but I'm showing you here with numbers. So we know that if we correct for all the observational bias, we know that there's a bias, right? That we are seeing more massive planets, we are seeing only certain kind of things. And therefore, if we actually correct for the biases, we'll see that 50 to 80% of exoplanets lie in this region, okay? 10 to 50% lie in this region. This is the Jupiter types, right? So 10 to 50% lie over here, and the bulk of them lie in this region, okay? They lie in this region. So what we actually see is the position of our solar system planets, for example, Earth, Mars, and Jupiter. It is not where the bulk of the planets of the universe seem to be lying. So there's something different about our solar system planets. It's not that it's unique, but it's not very common, the kind of parameters we have for our planets, right, compared to what we find in the universe. We just move to orbits of extrasolar planets. So if we were to look at the orbits of extrasolar planets, we can see the orbital eccentricity. you know that our planets, right, in our solar system, they are almost in circular orbits, right? So the eccentricity is close to zero. So you can see this over here, the eccentricity is close to zero for planets of our solar system. But of the exostellar planets which we have discovered, a very large number of them have very highly eccentric orbits compared to our, compared to the ones in our solar system. You see, all of us, you don't have anything more than 0.2, and the bulk of them are, 0.05, 0.1, something like that. But in extrasolar planets, you do have a good range of them which have larger eccentricities. So if you were to actually plot their orbits, many of them have, these eccentric kind of orbits, right? And if you actually plot them from the distances from their stars, you can see that they are this thing, they have orbits of this kind, depending on their masses. This is scaled in terms of the mass of Jupiter. Okay. Similarly, I showed you this already, eccentricity versus this thing. And you can see that many of them are eccentric orbits. Other than that, a lot of these stars don't have a single planet around us, like the sun also has a host of planets. Many of these are multiple planet systems. And here you can see the plot is there of various planetary systems which we have near the sun. And you can see that many of them actually have more than one detected planet, right, with different orbital periods. The masses of these extrasolar planets also have a large range. The range, there's one which, the least massive one has a mass of about twice the mass of the moon, while the most massive one has about 30 times the mass of Jupiter. But you have this whole range, this thing. And obviously the biggest problem is in detection, right? So low mass planets are obviously hard to detect. We can detect the massive ones, but not the low mass ones. So, even in detection, we do have a problem. Hot Jupiters are obviously common, easy to detect, and we can actually find them. And that's what we do find quite easily. So of the planets which are, this is an older slide. This is, I think, of 2017. But what you can see in this case is that till 2017, you still had the bulk of detected planets, which are, the Jovian kind, Jupiter kind, which is 1,217. And they are much lesser, which are these kinds, super Earths, other type, and Neptunian kinds. But finding these types are obviously tougher to find because they are low mass. And as of January 2020, Kepler and test missions, they have identified a large number of this thing. So if you can actually, this is the video which I will not show you, but you can actually use this to find, this is actually showing us, this is a picture of all the planetary systems in the neighborhood of the sun. So this is the sun with our solar system. And you can see all these different planetary systems in the neighborhood of the sun. There's a large number of these planetary systems, all very close to us, right? And so now that we know how to detect them, how do we actually expect to find them, right? How many do we expect to find? And I'll just take a slight detour in this case, is that our understanding of the formation of the solar system, right, is what? Is the solar nebula hypothesis. That is, when the sun is formed, when the sun was forming, you had a protoplanetary disk around them. And in the protoplanetary disk, you had accumulation taking place of material which formed planets, right? And as this material accumulated, this part which formed planets, each of them formed individual planets, right? And therefore, with our present understanding of how stars form, stars actually form in giant molecular clouds. And in giant molecular clouds, like for example, this is the M16, the Eagle Nebula. What you can see is that if you have a giant cloud, James Jean gave out this theory that basically just by its weight, if it's a low mass cloud, then the weight is less, right? The gas pressure is large. But if you have a high mass cloud, then gravity is high, pressure will be low, and the cloud literally will contract on its own weight. But this obviously happens only in the condition of the cloud is very cold and dense, right? And that's when you actually can have a star forming. And as the star forms, the disk around it is what actually forms into planets, right? So I have another picture of here. Here's a dark cloud. You have gravitational collapse taking place. You have a protostar over here. As the protostar forms, you see that this disk around it is where actually the planets form, right? And this is our understanding of the formation of stars. So, and now we also have observational evidence. So what I'm showing you here, these are HST images. These are images from the Hubble Space Telescope. of actually very young stars. These are protostars, very young stars in the Orion Nebula. And what you can see is that these very young stars actually have disks around them, which are the protoplanetary disks where stars are forming. And you have various stars, these are various images of protoplanetary disks where actually planets are forming, right? And now we have another telescope called the ALMA. ALMA telescope is a sub-millimeter telescope which can actually give images of protostars. So this is a very beautiful image which is of TW Hydrae, which is of a protostar which actually shows the protoplanetary disk around it. And if you zoom into this part, you'll actually see how planets are forming. And here I can show you with ALMA, the telescope ALMA. These are real pictures. These are real pictures of protostars, or very, very young stars, where you can actually see planets forming. So these planets are in the form of lumps, right? So you can see lumps around the star, and the lumps is where you actually have planets forming. So now it's not only through theory, but through observations also, we do have evidence that when stars form, planets form along with them, and they are actually observable. And therefore, we can actually say that planetary formation is actually a byproduct of star formation. And so if planetary formation is a byproduct of star formation, then planets should be common, right? That means almost every star should have a planet. Obviously, like I told you, I mentioned earlier that if the star is too hot, then in that case, the star may not have planets because it just evaporates all the gas and dust around it. But if the star is cooler, right, like the sun or cooler than the sun, then it can very easily maintain a planetary system. And we don't have time to talk about that today, but essentially the bulk of stars in the universe are colder stars. Low mass stars, colder stars form the bulk of the stars in our galaxy or in our universe. And therefore, since these are the stars which are actually going to house which are going to have planetary systems, that's exactly where we actually have to look for them, right? So we know that cooler stars are the ones which will have planetary systems, and that's exactly what we have. The majority of stars are like that. So we do have reason to look for planets. So what's the ultimate plan? The ultimate plan is we look for exoplanets, right? Once you detect an exoplanet, the next important step is to check for habitability, right? So I'll just talk about that in a minute. What is habitability, or what is the habitability zone? The next thing which one would like to do with that is spectroscopy, right? That is, you would want to know the chemistry of that exoplanet. You would like to know what is present in the atmosphere of that planet, so that could be where you could have these planets, right? And then you will actually look for signatures of life. And then the last final stage would be the contact stage, right? So if you actually look for the sun's closest neighbors, I actually showed you that image earlier of the objects near us. So we know Alpha Centauri with Proxima Centauri, there are already planets over here. So this is very close by. This is where within 4 light years, we already have planetary systems. And we are then also looking for planetary systems within our neighborhood. Some of them I showed you in that earlier image. Now, so once you detect an exoplanet, the important thing is to find what is called the Goldilocks zone. What is the Goldilocks zone? Is that, for example, if you have a star, if a planet is too close to the star, it's going to be too hot. If the planet is too far away, it's going to be too cold. And therefore, it has to be in a region which is not too hot, which is not too cold, which is just right, which is like it worked with Goldilocks. If you all remember the story of Goldilocks, where the porridge was just right, not too hot, not too cold. And that's the habitable zone, of which is just right? And that's exactly where you can have life. That means the planet is not too close to the star, not too far away. It is habitable, right? And that's the habitability zone. Now, if you actually, depending on stellar masses, the habitability zone will vary. Why? Because if the star is more massive, it is more hotter. And if it is more hotter, obviously the habitability zone has to be further away. So for example, this is a star which has the mass of the sun. So the habitability zone is somewhere over here. So you see Earth is very much within the habitability zone. Mars is towards the edge over here, and Venus is towards the edge over here. So therefore, Venus and Mars are the two potential planets where we actually look for life, right? Venus and Mars, because they are kind of in the edges of the habitability zone. Mercury is a bit too hot, and these guys, Jupiter, Saturn, Uranus, Neptune, are a bit too far away. So these only Venus, Mars are the ones where we look for life as we understand life to be, right? But if you have a star which is of lower mass, right, then the habitability zone is going to be closer to that star because the star is not so hot. And therefore, if you want the right temperature, often the habitability zone is also defined as the region in which water will be in liquid form, right? I mean, assuming that life needs water to drink, right? So then in that case, if we want water in liquid form, then in that case, that will be over here. And so this habitability zone is located over here. This star is much lower mass, and therefore you see the habitability zone is much closer. So depending upon the mass of the star, the habitability zone will vary, right? Now, if you see over here, if we actually look for the sun-like, if we actually see, this is the kind of region which we can get. But as we look for, as our detection methods are improving and we look for lower mass stars, we can actually find more stars in this habitability zone. So here you can see some are marked. You see these are the other exoplanets, some which have been found, which we know lie within the habitability zone, right? These guys lie within the habitability zone, right? Some of you all must have heard about the TRAPPIST system, which was discovered a few years ago. And you can see the TRAPPIST system has 1, 2, 3, 4, 5, 6, 7 planets. And you can see that these 3 are kind of within the habitability zone. And that's why people were very enthusiastic about the TRAPPIST-1 system, because you had these 3 planets which were very well within the habitability zone of the star. And this is not the only one. We have a whole bunch of potentially habitable exoplanets, Proxima Centauri B, there are various Tau Ceti, etc. There are a whole bunch of, these are the TRAPPIST system. There are a whole bunch of planets which we know which are within the habitability zone. That means, like I said, the region in which water would be in liquid form, right? Life as we know it to be. So these are potentially existing. But one thing I wanted to mention, which is very important, which was a dialogue given by Michel Mayor, right? Often people think that we are actually looking for exoplanets basically to go and colonize them, right? That because we are messing up our home planet so much, and therefore we are going to find this very green, lovely planet where all of us will go away after we have totally, spoiled the environment and the climate of the Earth. But this is one very, I like the statement very much, which was made by Michel Mayor after he got his Nobel Prize, where he actually said that we'll never colonize exoplanets, right? People should never think of it that we are looking for exoplanets to look for an alternate home. It is not an alternate home, right? We should not, it's not going to be that, because finding a home like the Earth is close to impossible, because you see the variety of planets, but for them to have conditions which actually suit us is something very, very, something very rare or quite impossible, right? So I will conclude with, this is a very beautiful plot again from, this is a shot from Voyager of the Earth. And you can see that there's a pale blue dot, which Carl Sagan wrote about, where, so from the Voyager mission, when they took a shot, that was the Earth. And that's what he said, that look again at this dot, that's here, that's home, that's us. And that's our home, and that's basically justifies why we need to preserve our home, because exoplanets are not exactly what we are looking for to colonize. It is part of our curiosity for life in the universe, for habitability in the universe, etc. But it is not going to be our option, right, as such, that we are going to colonize other planets. So I'll wind up with a few takeaways, that very likely all stars, or nearly all stars, a large number of stars, do have planets, right, based on our correct detection rates. And a few of these planets are definitely going to be Earth-like, and at least tens of millions in the Milky Way itself. There are various space-based, ground-based missions which are actually looking for or studying these exoplanets. Hot Jupiters are obviously easy to find, but there are various big planets further on, and some with highly eccentric orbits. The field is very fast changing. There are new discoveries every day, like, every day there's a new update on the number of exoplanets that have been discovered. And there's a lot happening in this field, and it's a very interesting field in astronomy to actually study this, right? So if you actually see on the NASA website, they've actually put up these travel posters, for traveling to exoplanets, where this is if you want to travel to 51 Peg, or this is another exoplanet called Kepler. And Kepler's this object is 186F, where the grass is always redder on the other side. It's a red giant, the star for it. And here you have Kepler 16b, where you basically have a binary system, Tatooine-like, and therefore you will always have a double shadow. So I'll end with this, and I'd be happy to take questions.
Yeah. Thank you, ma'am, for this wonderful talk. Really interesting. Thoroughly enjoyed it. So we have the question, can we live on the other than Earth? You really talked about it and how observationally we can practically sense. So thank you for this. And we are very grateful for you took all this session and lightened up your knowledge. It was really pleasure to listening you. Now I think we will wait next time to hear you again. So there are some questions in the chat box. So please go quickly through them. Thank you, ma'am.
Yeah. So there's one question on Tabby Star. Okay, I'll start from the beginning. Saurabh Sharma is asking me about Tabby Star, if possible. So Tabby Star is a star in which there's a very strange variation in the brightness. Okay, and therefore people, the problem was through natural explanation. It was very difficult to explain why do you have this kind of a variation in brightness. The fall in brightness was very distinct. So people had a theory that probably it is some kind of alien megastructures which are being built on that thing, which are actually causing this dimming of light. But as of now, we still don't have any good explanation for this thing. So Tabby Star does show a strange light curve, which we cannot explain as of now. Like I said, people have tried explaining using alien megastructures, etc. But we do not have, we do not know very well. Sri Suman is asking me, in case of micro lensing, we can see multiple images of one app. Yeah. So yes, in micro lensing, what happens is, depending upon the amount of bending taking place, you can have multiple images. But the problem is that a planet does not have a very large mass, right? And therefore, the bending which happens because of planets, for it to actually give multiple images is a little rare. What is more often is just the smudging, the light getting spread. And that is more common rather than getting multiple images. Multiple images very easily happen, for example, in galaxy clusters. In galaxy clusters, you could have a large number of galaxies with large amount of mass, which can, give a good enough gravitational effect for this. But in the case of, for a planet to do it, it's a little difficult, right?
Ma'am, can I ask?
Yeah.
In case of quasars, there is rapid variability, so we can see multiple image. So if Chandra have the very good spatial resolution, then we can distinguish by the Chandra telescope.
Yeah, you can do that, but the Chandra telescope basically observes in X-ray. It doesn't do it in optical, right?
Okay.
So
in the case of optical, there is any method to differentiate between them?
Look for it in optical. Using optical telescopes, you can actually do it. We have actually even tried doing it with the Himalayan Chandra telescope, which is our Indian telescope, where we actually use micro lensing to look for planets. We have been doing that, but it's a difficult job because the problem is for every star, you'll need to have a light curve, and you'll have to rule out all other possibilities as to why you're getting that, so that you get it. So it's difficult in the sense of the precision. And the precision, the difficulty is because a planet is not so massive, right? So it's not a very powerful gravitational lens, right? So that's why I was saying galaxy clusters are more powerful gravitational lenses. They give you a much better lens effect. But a planet is not such a powerful, this thing.
Okay, thank you, ma'am.
That's the problem with that. I can see there's another question by Ranjit. When you say that the majority of the star formation cloud is cold for the formation of planets, is this based on empirical findings or based on theoretical calculations? Okay, so essentially it is on theoretical calculations that you will expect that that's only when the gas and dust can, form. But now, because of ALMA data, I showed you images of ALMA which showed protoplanetary disks. So using ALMA data, you can actually see that, you can get the temperatures. because ALMA is basically seeing emission in the submillimeter, right, which are reasonably cold objects. And therefore, you actually can get proper measurements using ALMA data for the temperatures. So now it is both, Ranjit. Now it is both. We know it through our theory as well as now with ALMA observations, both of them. Right. Yeah, okay. I don't see any other questions, Shri.
Hello, ma'am. Excuse me. Ma'am, I have two questions, if I may ask.
Yeah, sure.
So, ma'am, you told about the JWST. When I also did read that one part of its mission is to look for exoplanets and like in this particular domain. But the thing is, like we know that it is made particularly to work in infrared space. And you also mentioned that transit-based method seems to be the most promising method for exoplanet detection. So, how is there any infrared-based methods also? Or like JWST, as you mentioned, like it is not made to search for it, but we jot down the data and look to a particular planet. So how is it, like, is there some method that I mean we don't know or something? And the second question is like something very generic, that you told that we have some 4,000 exoplanets right now that we have detected, but what can act as a proof of life in particular or water in particular, because visiting them may not be a viable option, especially with the current technology. So, like, what kind of work is being done for that?
And I'll repeat what you also said, that JWST's job is not to search. Okay, so there are telescopes which are called survey telescopes, which survey the sky, right? While there are telescopes like JWST, this is a very big telescope, and therefore it's only going to do targeted observations. So the idea is that you use Kepler data, or you use TESS data, or you use ground-based telescopes data, with which you get light curves, and you look for potential exoplanets. Okay, so using that data, if you have potential exoplanets, so like I said, the condition is that the dip should be at least 1%, right? And you should at least have three dips, right? And based on that, so that's counted like a 3 sigma kind of a detection, that you're getting 3 dips, right? So what happens is we use other telescopes to actually identify candidate exoplanets. Okay, and once we have the candidate exoplanets, then you use JWST to observe them. And then what JWST is not going to do to verify whether it's an exoplanet, it's going to, for example, do spectroscopy of that exoplanet to tell you what is the atmosphere of that exoplanet to be like, right? Or it is going to do, supposing it's doing radial velocity spectroscopy, it will use that to get velocities. Based on the velocity, it can get your mass estimation, mass radius estimation for the exoplanet, so that you can, then work on it. Like I said, mass and radius, the combination gives you density of the exoplanet. And you want density of the exoplanet to know the nature of the exoplanet, right? Whether it's a gaseous thing, whether it's rocky, whether it's whatever. If you have mass and radius, then m by r squared will give you density, and you can characterize the exoplanet, right? So JWST will do more the job of characterizing. So the work that has to be done before JWST, or to couple JWST, is the finding out of potential candidates. How do you find potential candidates? You actually use Kepler data or TESS data, or I showed you all some plots even of using ground-based telescopes, even a 16-inch. You can actually use that and look for signatures of exoplanets, right? The other question you were asking me about infrared. So actually, infrared is a very good region to actually look for exoplanets, because all of you all know black body radiation curves, right? So since stars are hotter, they are going to emit more in ultraviolet, right, in the blue side. But planets are colder. They don't have an energy source. They just reflect, right? And therefore, they are going to emit more in the infrared. And therefore, infrared is better to search for a planet than optical or ultraviolet, because in like I told you, right, in direct imaging, the problem is the difference in the brightness of the star and the planet. Now, if the star is going to be super bright and the planet has very low brightness because it does not emit, it only reflects, right? Then finding the planet in the light of the star is very tough. But in infrared, since the star emits more than since the planet emits more than the star, because it's a cooler object, it is good to look for infrared. So actually, infrared is very useful. Some of the images I've shown you were actually images in infrared to look for planets. It's better looking for planets in infrared. ALMA is in millimeters, so it's even further infrared, it's beyond. So longer wavelengths are better for searching for exoplanets compared to short wavelengths, because these are cool objects. These are not hot objects. I hope that covers the first question. The second question you were asking me was about life, right? So that's why I was telling you the steps. The steps is you first find the exoplanet, right? You characterize the star. You know the position of the exoplanet. You know whether you find out whether it's in the habitable zone. Then you preferably do spectroscopy to find out the atmosphere. And then there are what are called biomarkers, right? There are different kinds of elements, the presence of which indicates life, right? But that's a very tricky thing as to how reliable your biomarkers are, right? For example, when the phosphine problem was with Venus, phosphine was being used as a biomarker, but it is not very simple to identify biomarkers. So that is a tough problem of then getting it. And then we are also constrained by our understanding of life, right? So our understanding of life needn't be the only kind of life in the universe. So it may still not catch all kinds of life forms, right? So that's a tricky question to which we do not have all answers about finding life. But like I said, the step-by-step approach is this. You look for exoplanets, look for habitability, look for characterization, spectroscopy, and move like that. But it's a tricky question, right? It's tricky looking for life.
Yeah, thank you so much, ma'am. Got it.
Yeah. So Ranjit, when you say that majority of star formation is cold for formation, okay, I answered that already. Ranjit is another question. Does it make sense to use Kepler and TESS data to detect new exoplanets for various? Yeah, definitely. Because the problem is that there's so much of data from Kepler and TESS, so much. See, basically it means that for every star that it has observed, you have to plot the light curve. And then you use the light curve to actually fit it and find out parameters. And obviously the number of stars that have been observed by Kepler and TESS are much more than the number of astronomers who are looking at the light curves. And that is why, like I said, there are citizen science projects, like there's one called Planet Hunters. There are various projects like that, where they're actually asking citizen scientists to actually look for planets. Other than that, all the data of Kepler and TESS is available online. So any student at a point of time can download the data, plot it, and look for it, right? So there is still lots of data available which still needs to be analyzed, and these are all going to build up your candidates, not just for JWST but for any other telescope. If you want to do spectroscopy, you want to know the candidates, right? So you identify candidates best using Kepler TESS data, because that is space based, right? It has the best precision in photometry, right? So that would be the best quality data possible, right? So Ranjit, I hope that answers your question.
Yeah, thank you very much. And also I have one question. So this spectroscopy you have talked about, so what is the prospects? Like, it seems to be like exoplanets, they are very faint, so you are not getting many photons, and then doing a spectroscopy seems to be a very difficult task. So will there be any future missions dedicated with the spectroscopy or something?
Yeah. So James Webb is also there, which with 6.5 meters, it hopes to collect more light. But even James Webb will only be able to do it to a certain distance, because like you said, spectroscopy, you're taking light only within a certain, small window.
Yeah.
And in that window, if you want to then do spectroscopy, it's obviously very difficult, especially for a planet, right?
Right.
Because, so it's actually a very difficult job. So it will be done only for certain exoplanets. It can't be done for example, it will be done only for exoplanets within our galaxy. We definitely cannot look for outside. But even within the galaxy also, there'll be limitations. So spectroscopy of exoplanets is still a tough job. But I hope you're aware that a whole bunch of ground-based telescopes are coming up, which are 30, 40 meter class. And like, ELT, TMT, all these other ones. And these will also be doing things like that. But obviously, it's a tricky job. It's difficult. It's not very easy.
So then, let's say you find an exoplanet which is in the habitable zone, then what is the next step or strategy to find out whether it's actually there is something called life there or not?
Yeah, so one step is you look for biomarkers in the spectroscopy, right? You look for biomarkers or signatures of life. And I don't know whether you're aware of, the breakthrough, this thing. They actually had proposed the Starship mission, where you send these light sails and you go send it to Alpha Centauri, because we know Proxima Centauri already has a planetary system.
Right.
That is 4 light years away, 40 light years away. So it has to go and come back, and then we'd get some shots, literally photographs of the thing. But, it sounds quite science fiction-y, obviously.
Yeah, right.
So
Really ambitious, yes.
it's actually, see, if you even go on in a plane on the Earth, right? At what height do you actually detect life on the Earth? Even at 10 kilometers height, you actually don't detect it as such, right?
Okay.
And it's very tricky. It's a difficult problem, because, like I'm saying, even when we are still searching Venus and Mars only, we are going mad with that, right? We still don't have answers to Venus and Mars.
That's true.
Looking at extrasolar planets.
Yeah.
So, tricky job, difficult job.
And hope JWST will give us some clue or some evidence, like, okay.
Yeah, but I think we should not have too much of expectation, because,
Right.
like I said, it's a difficult thing. It's difficult, right?
Yeah.
So I don't know, but we probably will get something.
Yeah.
But there are a whole bunch of other projects also which are there, exoplanet ones through ESA, NASA, and all that. There are other ones, but yes, it's difficult. But the thing is, there's a lot of interest in it. Everybody's interested in it. Everybody wants to know it. So you can get good funding if you say you're looking for exoplanets.
Wow, that would be nice.
Yeah. So.
Okay, so anyone else have any question? Just let me